Hello and good morning, good afternoon and good evening, just depending in which time zone you currently are. My name is Andreas Henk and I work in the Institute of Applied Geosciences at the Technical University in Darmstadt, Germany. Just to give you an idea where Darmstadt is located, I guess most of you will know Frankfurt in central Germany, at least the airport from a stopover, and Darmstadt is located about 25 kilometers to the south of the airport. My research interests focus on numerical modeling of geological structures and processes using thermal, hydraulic, mechanical and coupled simulations on different spatial scales. I have worked on generic examples and real-world case studies located in a variety of tectonic settings, ranging from continental rifts and passive margins to fold and thrust belts and origin. But today, the main focus is, of course, on strike-slip terrains and transform margins. I'm sorry that I'm not able to be with you in person, but please feel free to send me an email if you have any questions regarding this presentation. So let's start. In the webinar today, I will talk about the temporal and spatial evolution of thermal regimes along transform margins and how thermal kinematic modeling can help to provide a quantitative and process-based understanding. This modeling study was motivated by the fact that the thermal histories of transform margins are fundamentally different from those of extensional margin settings. In case of a rifted margin, where movements are orthogonal to the ocean-continent boundary, a seafloor spreading center develops parallel to the margin at the time of continental breakup. During the subsequent drift stage, this oceanic ridge progressively moves away from the continental margin, and hence the thermal anomaly induced by the rifting event decays over time. Although there is a temporal evolution in the thermal regime, it is the same for all points A, B, C having the same orthogonal distance from the margin. This differs fundamentally from the conditions encountered at a transform margin, where movements are primarily parallel to the plate boundary. Following continental breakup, the spreading center and the related thermal anomaly due to stenospheric upwelling moves parallel to the margin. This results in a very variable local thermal history, just depending on the position, both orthogonal to the ocean-continent boundary and along the transform margin. Have a look at location A, which experiences a single-phase thermal evolution comparable to the normal rifted margin setting. In contrast, location C experiences a thermal evolution with two peaks, one at the time of rifting and one when the traveling spreading center passes by. Such general qualitative conclusions can already be drawn from this sketch. However, in the real world, and for any quantitative predictions of the thermal regime, the specific local conditions have to be considered. Major factors controlling the thermal evolution of a particular transform margin are the margin geometry, in particular the length of the transform fault between the two offset ridges, and of course the spreading rate, which controls the timing of ridge migration. Thus, no two transform margins will be the same regarding their thermal evolution. These complexities have to be kept in mind, especially if the hydrocarbon potential of sedimentary basins located at transform margins is assessed. In order to get a quantitative understanding of the variable temporal and spatial evolution in the thermal history of a transform margin, and to derive data like heat flow over time, which then can be used as boundary condition for special basin and petroleum system modeling approaches, we apply a thermal kinematic modeling, approach based on finite element techniques. This approach assumes 3D heat transport by conduction and advection. The governing equation is shown here on the upper right and uses specific thermal parameters like thermal diffusivity, defined by density, thermal conductivity and specific heat, as well as radiogenic heat production for each of the 6 model units. These 6 model units are the oceanic sediments, the upper and lower parts of each, the continental and the oceanic crust, as well as the mantle lithosphere. While the advective part in the equation accounts for migration of the seafloor spreading center, heat transport by hydrothermal convection in the uppermost part of the oceanic crust is approximated by increasing the thermal conductivity in this layer using a Nusselt number of 4. The model geometry used in this study is inspired by the Romanche transform fault, which is a rather large structure with low spreading rates, which promotes the temperature effects we are interested in. Model dimensions are 860 kilometers by 150 kilometers and a thickness of 75 kilometers, and the entire model is centered around the transform fault. For the numerical simulations, this model geometry has been discretized in about 43,000 elements. Thermal boundary conditions are a constant surface temperature and a temperature of 1300 degrees C at the model base, representing the lithosphere-asthenosphere boundary. This results in an undisturbed equilibrium heat flow of about 71 milliwatt per square meter, a value close to the global average for the continental domain. Asthenospheric upwelling in relation to oceanic rifting is described by assigning 1300 degrees C also to the mantle right beneath the ridge. The kinematic boundary conditions describe the advective heat transport component caused by the movement of both the ridge and the newly formed oceanic crust relative to the fixed rear part of the model. It considers that one half of the newly formed oceanic crust becomes part of the fixed model domain, whereas the other half is displaced with the moving plate in the front. In the present study, a spreading velocity of 3 centimeters per year is assumed, which is typical for the Central Atlantic, but rather slow in comparison to other ridges worldwide. The figure on this slide shows the lithospheric temperatures from continental breakup until 70 million years after, as provided by the thermal kinematic simulation outlined before. For the ease of visualization, the frontal model parts, so the moving plate and the newly formed oceanic crust attached to the fixed plate in the back, have been removed. So you now can see easily the elevated temperatures induced by the traveling ridge, which decay with distance and time respectively. At the time of continental breakup, the asthenospheric upwelling causes prominent positive thermal anomalies in both rift segments linked by the transform fault. As seafloor spreading moves the ridge away from the rifted margin segments, these regions experience post-breakup cooling. During the subsequent ocean-continent transform development stage, heat conduction from the adjacent oceanic lithosphere becomes important for the temperature of the transform margin on the leading side of the traveling ridge. Due to the passage of progressively younger and hence hotter oceanic lithosphere, the continental side of the transform fault experiences some post-breakup warming. It ultimately leads to the thermal peak, which occurs when the ridge passes by. After ridge passage, the transform margin undergoes cooling due to thermal equilibration. As drifting proceeds, the traveling ridge and the related thermal anomaly in the transform margin reach a position opposite to the second rifted margin segment which had formed during initial breakup. Thus, following a first thermal peak, which occurred at the time of breakup, this area now experiences a second heating phase. This is shown if you compare these two modeling results in the area of 50 million years and during initial breakup. After the ridge has bypassed the continental margin and continues its movement in the oceanic offshore, both the rifted and the transform margin segments undergo lithospheric cooling. Similar relationships can also be observed in the surface heat flow, which is a good proxy for the temperature distribution in the lithosphere and which can also be used as an input parameter for source rock maturity studies. During continental breakup, surface heat flow values in excess of 150 milliwatt per square meters are reached in the immediate vicinity of the two successful rift zones, shown over here and here. During the subsequent drift phase, lateral heat flow from the traveling spreading ridge, as well as from the newly formed oceanic crust, warms the adjacent continental lithosphere across the transform fault. Substantial increases in surface heat flow exceeding 80 milliwatt per square meter are counted in a 30 kilometer wide zone of the transform margin adjacent to the transform fault. And this heat flow normally travels with the migrating ridge, as can be shown here in the modeling results. At the same time, the continental lithosphere on the trailing side of the migrating ridge shows decreasing surface heat flow values caused by thermal equilibration and cooling respectively. This process ultimately leads to a second heat flow peak in the areas of the rifted margin formed during earlier continental breakup. During the subsequent activity of the ocean-ocean transform, surface heat flow values in the entire continental domain undergo a progressive decrease due to thermal equilibration. In a strip parallel to the boundary of the transform margin, this region here, heat flow values even lower than those that existed prior to rifting can be observed. This results from crustal thinning along the transform margin, as well as the lateral heat transport from the continent towards the cooling oceanic lithosphere, which undergoes very effective convective heat transport and only has a neglectable radiogenic heat production in this domain. The spatial variation in surface heat flow over time can also be shown by looking at different points along the margin, each having the same orthogonal distance to the transform fault. The red dot marks the location for which the red curve shows the heat flow evolution. The continental rifting stage, ultimately leading to breakup, results in this increase in surface heat flow, which afterwards decays with time, ultimately leading to the somewhat lower equilibrium surface heat flow than the initial one for the reasons I've just explained. The orange to light blue curves for points along the transform margin nicely illustrate this pre-warming effect mentioned earlier, as the heat flow peaks gain height and get broader with time since breakup and with distance along the margin, respectively. This is because on the leading side of the ridge, lateral heat input from the migrating continental lithosphere heated during breakup and from the cooling oceanic lithosphere, which gets progressively younger and hotter until finally the traveling ridge itself arrives. And all these effects together raise the temperatures on the continental margin side. For this hotter lithosphere, it then takes longer to equilibrate thermally, and that's why these peaks are wider. Finally, the blue dot and the blue curve stand for a point at the second rift segment which experiences these two thermal peaks, one at the time of breakup and one at the time when the ridge passes by, which in the present modeling study is 50 million years after breakup. In between, this pre-warming effect already ensures increased lithospheric temperatures and longer times for thermal equilibration afterwards. These two extremes of a single and a two-phase thermal evolution can also be observed by looking at points with different orthogonal distances to the transform fault. In the figures shown on this slide, the red curves stand for points which are located in the continental domain next to the transform fault, whereas the blue curves show the surface heat flow evolution for points at about 75 kilometers orthogonal distance to the transform fault. Again, the locations near the rift zone in the back of the figure show the single heat flow peak for breakup only, whereas the points near the second rift zone in the front experience two heating phases, one during breakup and the second one during passage of the ridge. The modeling results show that even areas inland of the transform fault are affected by the processes happening at the transform fault itself. They show a similar heat flow pattern, also at reduced absolute values. There is, however, a certain delay in the thermal peak due to the slow conductive heat transport, and this delay increases with increasing orthogonal distance from the transform margin. If you remember the sketch I showed at the beginning, these modeling results show quantitatively how there are substantial variations both parallel and orthogonal to a transform margin, not just perpendicular as in case of a rifted margin. So to wrap up and to come already to the conclusions of this short presentation, the modeling results nicely illustrate the effect a spreading ridge moving along a transform fault has on the thermal regime and how this migrating heat source results in spatially as well as temporally quite variable temperature and heat flow patterns. As a rule of thumb, one can state that the longer the transform margin and that the slower the spreading rates, the more pronounced the spatial and temporal variations in the thermal regime are. For quantitative prediction, however, the thermal kinematic modeling approach shown in this presentation offers a toolbox which can be adapted to any particular transform margin setting. It can then consider the specific local conditions, not only regarding thermal properties, but also regarding transform fault lengths and spreading velocities. Such a thorough understanding of the complex heat flow patterns which occur at transform margins is relevant not only for source rock maturity studies. This is of course the most obvious application, but it is also of importance to understand the migration of depot centers as well as the migration of uplifted areas along the transform margin, which may get eroded and provide detritus with different provenance for the reservoir rocks. And last not least, the variable temperature fields will also have a strong effect on lithospheric strengths and ductility patterns in the lower crust. Thanks for your attention, and as I already said at the beginning of the presentation, just send me an email if you have any questions.